What the heck? It's a video key. Okay, dynamic equilibrium occurs when the... Oh yeah, I gotta touch a thing here. When the rate of dissolving, so something that's aqueous, is precipitating at the same time. So dynamic equilibrium means equal. So dynamic equilibrium occurs when the solute dissolves at the same rate as the crystals precipitate. So that is C. Okay, next question. Bye-bye. Okay, which of the following statements best defines or describes a saturated solution? Okay, a saturated solution is simply a solution at maximum concentration which no more solute will dissolve. Okay, this is partially true as well, but it's not a solvent, it's a solution. All right, moving on. Which of these will undergo complete dissociation? Dissociation only occurs with ionic compounds and ionic compounds that are soluble. That is the only soluble ionic compound. Which of the following is a soluble molecular compound? That's an acid that is ionic. So now we're down to 2 molecular compounds. The only one that dissolves is glucose. Which of the following mixtures could contain ions? Could contain ions. So sugars are moleculars. They do not form ions. 2, salts dissolve, make ions. 3, acids can make ions. And 4, bases can make ions. So that could be right. That one can't be. That one can't be. And that one can't be. So the only one that's correct is 3 and 4. Yes, 2 is right, but the only possible correct choice is that first bubble. Okay, which of the following is a gas in liquid type of solution? So which one is gas in water? It's bubbly carbon dioxide. A solution that is a relatively large solute dissolved in the solvent, so solute is the solid, solvent does the dissolving, is concentrated. If you watch the lab with Zelinsky and I, Z-Dog, which piece of lab equipment is used for preparing a precise volume of solution? That's a volumetric flask. It's one of these guys, right? Okay. When making a standardized solution, always add the mass directly to the flask. No. The mass directly to the beaker. No. The total volume. No. Half. Mass to half the volume. That way you don't make a mistake and add too much water. What volume of water should be added? Oh, this is going to be a salty question for some of you. Yes. You have to do C1, V1, C2, V2. Okay. So we have 500 mils and 1 mole liter to start with. So when we times it out and turn that to liters, and we're making concentration of 0.5 and finding volume 2. When we find volume 2, and by dividing both sides, right, we're going to get, so did I set this up right? 1 second. Should be, I missed the dot. That's what it was. It looked weird. I knew that looked weird. Okay, so when we divide this out, we get 1 liter, right? Now, a lot of people picked this answer. Now, you're right, that's the total volume, but it says what volume of water should be added. So if we start with 500 milliliters and we're going to a liter or 1,000 milliliters, we have to add 500 milliliters to this to get to that final volume. So that's why it's 500. I know, that's a mean question. A bottle contains 3 moles of 12 mole per liter sulfuric acid. Half of it's spilt. Well, if you spill acid, it has the same concentration. The concentration doesn't change. Because it's like if you're drinking a nice glass of orange juice and you spill it all over the counter, but there's half left. The taste of the remaining orange juice doesn't change. It's only when we add water that we dilute it. Okay, which of the following contains 1 mole of copper nitrate? So if you want to find moles, you can quickly multiply the 2 concentrations together. So we have 0.5 liters, and if we times that by 0.5 moles per liter, the liters will cancel. And 0.5 times 0.5 is 0.25 moles. Now, you're going to have to do that for each of these questions. This is the one that gets you to 1 mole, because 0.5 or 500 milliliters is 0.5 liters. And when we times that by 2 moles per liter, half of 2 is 1. All right, what laboratory technician is laboratory? Okay, so this is what's the mass? This is a tricky question. Okay, this is a unit analysis question, and we need the molar mass of this compound. I know it's written really weirdly. So we have 1 copper, 6355. We have 1 sulfur, 3207. We have 4 oxygens, and then we have 5 waters. That's also included in the molar mass. Okay. So when I add up all of that, I get 249.72 grams per mole. Okay. Now if I multiply that by 0.5 moles per liter, and moles are going to cancel, right? I'm using that value there. And then 0.250 liters over 1, the liters cancel. Now when I multiply all that together, I get 31.2. A lot of people got 20. I think it's because they forgot the molar mass of the water. We did do that in the lab, if you remember. Okay, in the lab we had a hydrated compound. Okay, what is the amount concentration of strontium ions and hydroxide ions if something dissociates of strontium hydroxide? So if we have strontium hydroxide, and a couple astute students realized that wasn't soluble, so I'll have to change that for next year. But if it was to break up, it would break up into 2 hydroxides and 1 strontium, and we would have 0.5 there. These are in the same ratio, so this would also be 0.5. Going from here to here, we have twice the amount, so it would be 1. So how much strontium ions are there? 0.5. How much hydroxide ions? 1. So the correct answer is right there. Okay, the concentration of ammonium ions. All right, this is a very challenging problem. And I made it a bonus question. Okay, so ammonium sulfide looks like this. Some people didn't write it correctly to start with. Ammonium's +1 and sulfide is 2 negative. When that dissociates, we're going to get 2 ammonium ions and a sulfide ion. Okay. Now, it wants us to eventually find the concentration of ammonium ions, but it gives us mass of ammonium sulfide, okay, and it also gives us volume. So what goes with mass? The answer is molar mass. So we need to make a little toolbox of the stuff we need. We need the molar mass of ammonium sulfide. Okay, nitrogen is 1401, 404 times 2 is 3207. Okay, I get 6817. I'm just going to write down my stuff down here. 6817 grams per mole. Okay, I have 0.750 liters, and I have 25 grams. Okay, so I need to get to start with the concentration of this substance. So I'm going to flip the molar mass, mole over 6817 grams. Okay, I'm going to put the grams on top, 25 grams. I'm going to put the volume on the bottom, 0.750 liters. Okay. So when I multiply that out, 25 divided by 6817 times 0.70, I get 0.488, roughly, moles per liter. Now, that would round to 0.489. Now, you think, oh, that's the answer. Now, that's not the answer, because what I've calculated here is the concentration of this. I need the ion, and guess what the ratio is? Twice the amount. So that's the answer. I have to times that by 2, times by where you're going, divide by where you've been. Very tough question. All right, which of the following solutions does a decrease in temperature increase solubility? Well, we talked about that the colder a liquid gets, the better it is at dissolving gases. A gas dissolves within a liquid. The colder, if you tried to dissolve a solid in a liquid, you'd want to heat the liquid up. So it's opposite. Gases get more soluble the cooler they get. All right, we got this arsenic question. What's the mass of the arsenic? Okay, so there's a couple ways you could go about doing this. One is the parts per million formula. So we would go 1 we would go X, we're trying to find solute over 90.2 liters times 10 to the 6 is equal to 14.3. I'm going to divide both sides by 10 to the 6. And I'm going to times both sides by 90.2. Now, that is going to give me X in kilograms. Okay, it's probably going to be a pretty small number. Let's check it out. Divide that by a million times by 90.2. Yeah, I get X is equal to 0.001289, blah, blah. And that's what a lot of people picked. They stopped here. But the thing is that in parts per million and percentages question, the units on the top and the bottom are the same scale. So the unit on the top being a kilogram is not what the question wants. The question wants grams, so we have to times that by 1,000. And we get 1.289 or 1.29 rounded. So that's the right answer. Okay. Okay, tooth decay. Tooth decay question. This is a mole ratio question. Okay. So it says we have 2 moles of calcium, and we want to find the phosphate ion. So we times by where we're going, 2 times 3, because that's what it's balanced for, divided by where we've been, 5. So I started at calcium ion, I'm going to the phosphate ion, that's 3 over 5. 2 times 3 divided by 5 gives me 1.2. Times by where you're going, divide by where you've been. Okay, the next one's very similar. The concentration of the phosphate ion is 2 moles per liter. The concentration of the hydroxide ion is times by where you're going, 2 times 1, divide by where you've been, 3. I said that's balanced for a 1. 2 times 1 is 2, divided by 3, 0.666666666666 round to 0.67. Okay, continuing. Breathalyzer. All right, so there's a couple ways you could solve this one. I thought it would probably be faster to just figure out what your percentage is. So here's one way you can get it, right? You can go 0.08, figure out what the percentage, it's grams, figure out what your decimal is, so 0.08 divided by 100, okay? We get 8 times 10 to the minus 4, okay, or 0.0008. Then I'm going to times that by 7,000 milliliters. Because what this is basically doing is, you know how this would be a percentage? Right now it's a decimal, so I times that by 7,000, and I get 5.6. Now, that's a shortcut. Here's how I kind of figured that out. The formula, I can't do that. The formula is solute over solution times 100. And that will get me 0.08%. So what you would do, that's the percentage of this system. The percentage in this system is identical. So you would just take 0.08% of 7,000 milliliters because it wants the answer in grams. You turn a percentage into a decimal, and that's what I did up here. That's why I had 0.008. And you do get 5.6. Okay, sports drink contains 50 milligrams of sodium ions and 55 milligrams in a 400 milliliter serving. What's the parts per million? Okay, part per million is solute over solution times a million. Now, we need to have the same unit on top and the bottom. Whoop, did something weird there. Let's click out of this mess. What happened here? Something weird happened here. Okay, I don't know what's going on. That's super weird. Okay. Anyway, so we have 50 milligrams and 55 milligrams, but our volume is in milliliters. Milligrams and milliliters are not the same scale. So you would have to divide your milligrams by 1,000 to get grams to have them in the same scale. So the first one would be 0.05 over 400 times 10 to the 6. And the second one would be 0.055 over 400 times 10 to the 6. So when we do that, especially for the first one, it's going to solve the question. We get 125. So the only system that works is that one. Okay. So milligram and milliliter are not the same scale. We did a question like that in practice. Okay, it's a dilution question, C1V1 question. Equals C2V2. Okay. We got to find the concentration of the final solution. So dividing both sides by V2. So throwing our numbers in there, our C1 is 6. Our initial volume is 100 milliliters, but let's turn that to liters, 0.1. Over our volume of the second system is 2. So 6 times 0.1 divided by 2 gets me 0.300, 3 sig figs. I hand marked all of these, so people who had weird sig figs, you got the right answer. Okay, a bottle of water stating parts per million. Okay, how much? What's the solute? So X. Whoa. X over 500 times 10 to the 6 is equal to 210. Okay, divide both sides by a million times both sides by 500. Okay. Now that's going to give us X in grams, because if we're solving for milliliters, right, milliliters on the bottom, we'll have grams on top. So 210 divided by a million times 500, that gives me 0.105 grams. But it wants it in milligrams, which means we have to times this by 1,000, and you get 105. Okay. Saline solutions, blah, blah, blah. Okay, what is the percentage? So a gram and a milliliter are the same scale. So this is a super simple question. 0.9 over 100 times 100 gives us percentage. Solute over solution. 0.9 divided by 100 times 100, which is really like not doing anything at all, gives us 0.900%. All right, the next question here had a couple right answers. The element didn't have a couple right answers. The only one that's an element is the one by itself, which is 3. Then we had a soluble ionic compound. That was if you had an ionic compound, you form ions. An insoluble molecular compound just doesn't become aqueous. So there was a couple right answers. 2, that could be wax. All right, another one, 5, you could have a gas. So 2 and 5 are both right. A weak acid starts aqueous and ends aqueous because it doesn't split up. So the last one is 6. All right, so next question. All right, so we need to solve for the mass of glucose. What mass of glucose at this concentration and this volume? So if we write down what we know, we got 4.7 liters, 7.88 millimoles per liter, and glucose is C6H12O6. So because we're solving for mass, we need the molar mass of glucose. Now I'm just plugging that into my calculator really quick. I get 18, that's 180, 18 grams per mole. Okay, solving for mass, I'm going to start with mass. 180, 18 grams per mole. Okay, I'm solving for mass, so I got to get rid of moles. Now you might say, hey, that's in millimoles. That's fine. Let's just leave it in millimoles because the moles are going to cancel out. And then I'm going to put 4.7 liters over 1, so the liters cancel out. So what I'm going to do is multiply the whole top. What is that number? 7.8 times 4.7. Okay. And I get 6,605 milligrams because the mill is left over. Milligram. Now, the answer is in grams, so I would divide this by 1,000 to turn it into grams, which is 6.6 or 6.61. I hand marked that. The sig fig should be to 2. And some people who did the quiz early, the key was wonky. So I made sure anybody who got close to an answer to that got it right. Okay, here's the Dr. Evil question. Now, you had to do this. I marked at a 2. You had to do the math, right? So if we're reading this question, he has a concentration of 1.55, and he's going to put it into a 5-liter bottle. He wants that final concentration. The first concentration is 4.90. So this is a dilution problem. So I need, jump down a bit. I needed, okay, I'm just going to have to erase this here. Screencast stuff. Okay, so the first part was the math. C1V1 is equal to C2V2. The concentration initial is 4.90 moles per liter. Dr. Evil doesn't know how much of that to take. The final concentration is 1.55 moles per liter, and the final volume is 500 milliliters. So I'm going to divide both sides by 4.9 to figure out the final volume. So that was the first step that you had to do, is figure out how much chemical Dr. Evil needed. All right, and we get 158 milliliters. Now, then you had to explain that you would take, Dr. Evil would take 158 milliliters of the concentrate and then dilute it to 500 milliliters. Like, do some kind of explanation of how you would actually make a solution. You would take the 158, add it to a second beaker or a flask, and dilute it to 500. And then you'd have a dilute solution. Okay. Now, last question was asking about errors. I was super lenient on this. You got 1 mark if you told me like you made a math error. That's fine. Now, the other marks came from overshooting the meniscus. So when you're making a solution, you have that meniscus line. If you go over, you're wrong. Okay. Other people said adding the whole mass to the water, not half the volume. So really, any kind of error that Zielinski and I talked about in that video was possible. And this has been the video key for the unit test.